going to be talking to us about data modeling in an event-centric world.
What we're talking about is how do we take those tools and skills that we have from all of our relational modeling, structures, and how do they apply in event-driven systems, in large distributed systems that need more than 3 or 4 cowboys to get things done, right? To start off, one of the things I find is that defining what we're talking about is the first real big thing we got. So what our goals are, simple scalable systems, what some of the enemies are, why do we care about, why do we want event-driven systems, what are we really trying to get to, and fundamentally, the enemy is complexity. And 1 thing it's simple, 2 things it's simple, 3 things and it's kind of hard to reason about. We start locking more and more things together. Eventually the business wants 1 more feature, 1 more piece of data integrated, we can't understand it. Right? So how do we fix this? Because this is what happens in production. Right? This is our relational database. And we look down at it, that's the central table in our database. Right, so this is what we're trying to solve. Right, this is a real world production system that makes a lot of money. It's a flagship system, but it's completely enmeshed in this world. And we work hard enough, we can do it with microservices too. Right? So this is where we're trying to get to. And so I was asked sort of tongue-in-cheek, if there was 1 thing you get a law that had your name on it, what would it be? Because what I came up with is 5 fully interconnected things nobody can understand. 120 connections, you just can't keep that in your brain. But we know that's not, we can fix it. Does anybody recognize what this is? This is 1 attempt to fix it. Classic 3-layered architecture, UI, business logic, data. We're trying to reduce the number of connections, simplify things. Does anybody recognize what this is? Same 5 things. CQRS, separating commands and
Chris,
queries.
can I just interrupt a second? The microphone's not doing what it should. Would you mind using that one?
Not at all.
Thank you.
Is this working now?
No.
Test 1, 2. Yes, no? Okay. All right, so this is CQRS, right? And all we're doing here is we're saying, these are writes, this is what we're going to store, these are optimized reads, this is what we're going to read. This is a logical model. It's not telling you what there's physically, right? This is in a relational database. There are normal form tables. First normal form reporting tables, right? Same thing. Because what this lets us do is build pipelines. If we have pipelines and it's 1 thing in and 1 thing out, we can always understand what's going on. So we want our data, our source of truth, our messages traveling in pipelines. And we want to keep what we're working on simple. Because then we can scale it out. I can have a cluster that gets wider or smaller, all dealing with the same thing, now with messages. So, we're trying to go from this interrelated mess to a series of events that we can track in a very simple straight line loop. So, we all know about relational storage. And anybody here actually used a graph database? All right, one, two people. Right, it's a specialty thing, but it's a different storage structure. And then, of course, there's document databases. Imagine more people have used Mongo, right? Done web apps, put your view state in there. Very easy to access, loose schema. There's one more type, which is actually older than the other ones, ordered storage, right? Who here has used ordered storage? Everybody raise your hand, right? All it is where you save things in order. Doesn't that sound like your logs? You know, anybody had a log from your application? It's ordered storage. You're writing things down in order. It's where we all started, append-only files, right? Now, first type of ordered storage is a log. List them in order. Then we have ledgers, right? And a ledger is each entry is a transaction. Blockchain is just a ledger that you put up in the internet with fancy, cryptography so you can't change anything, right? Same model. And the last one is event streams, where you're got a ticker stream of just facts coming out. So ordered storage is the crux of how we move forward with data when we're saving events. So we want to use an ordered persistence mechanism because it has a low impedance, fits into our pipeline of how we're working with things. So as we start doing this, the next thing that gets complicated but is actually very, very simple is people conflate the different application patterns that they're using here. So let's talk about the four. If I've got a warehouse, there's four ways I can record what's going on. Please add a box. My inventory is 80. I added a box. My inventory increased by 1. Right? So this is like change data capture stuff, commands and events. So commands and requests. If I save commands, I'm command sourcing. If I have a disconnected system, something like that, that's very good. It's very useful, but it isn't what happened. It isn't an event. Current state is a snapshot in time. I don't know why my inventory is 80. Is it 80 because I just did an inventory count and I realized 5 boxes walked away? Or did 5 boxes go in a truck? Or did I get shipment in? I don't know how I got that number, right? So I don't have any context for it. In deltas, change data capture is even worse. Like I have no idea why it went up or went down. So what I want to save, it's a decoupled thing. So without knowing anything about the warehouse, just looking at the database, I know what happened. So for data, that's what we care about. We want the event stream and the log, I'm going to say this a couple of times, to be independently understandable without needing the services, right? So let's talk about that. Well, so event sourcing is applications decisions versus an immutable sequence of business events. It's not a +1, -1. It's like blue jeans were put in the shopping cart. A box was added to this truck. This thing happened. We denied this person credit. It's a series of business events that have been decided that give us that history we can build our state up on. It's just like looking like a call stack when you're trying to figure out what's going on in a method. Here's how I got here. Does anybody recognize what this is? This is a Turing machine somebody built. So it has the tape, it moves back and forth. So this is the crux of event-driven state machines. We just run the tape one way, right? We turn it into a transducer. So if we have that as our little model, we have our service, which is internal state, input, output, and our history of events. So again, to go over our 4 models, if we're saving the input, we're command sourcing. If we're saving internal state inside our service, it's either state logging, snapshots, or change data capture, right? Both of which are taking internal state from our service and saving it. Now, if I have a different service, how do I know how to take 10 years of history of that and understand it? And if you think about it, version 1 and version 2 of the same service could have a different internal state and implementation. So it's not just a different service, it's even the same service over time gets enmeshed in understanding your data. So what we want to save is the output, the events, what was decided independently of the service about the business. And we want to model that as part of our domain. So let's talk about how a database that works this way really works. We're going to have our core log, which is all the events that occur, right? And then we have individual addressable streams, and these are going to map to tables, right? Same way you have a database, you don't have just a pile of things unless you're using a key value store, but even then, your history is divided. And we can have views or indexes that are separate. So as we add data into the core stream, it's dropped into an event. So this is equivalent to like the write-ahead log in Postgres. This is that core series of changes, and then these are the tables. But here we have events that we're dropping into streams that are going to line up with our services. Right? And we see the indexes has a different sequence of events. That could be like all exceptions or all finalizations, right? So now we get back to how our applications use this database. We're going to say that each service, each instance is going to operate on one stream, right? So when my service opens up and works on invoice number 1, there's going to be one stream for invoice 1. Invoice 2 will be in a second stream. Invoice 3 will be in another stream. But all those are in the master log. So I can always run a report and get total outstanding invoices, because the log has all of the data, but this service looks at this invoice, invoice 1, invoice 2, invoice 3 independently. And then all my reports, the readers, pull from any one of these. Do I want to have who's overdue, all those things. So is this model starting to make sense? We write things down in order, we align them to our services, we save the events in order. So that's the fundamental structure that we want to use as we're walking through building event-driven systems. This is a list of things that you want to have in those kind of systems. You want it to be a real database. Basically what it boils down to in a nutshell, right? So we go back here, as we look at this, having just a log and a series of streams, it's a pretty rough ordering of things. We actually want to have a more robust data model available to us than just a log of random events. So what we start looking at is creating categories. So I have an event log, I have a customer, which you see is an index for customer 1 and customer 2. And totally separately, I have invoices, I have invoice 1, invoice 2. And what this starts to build up is the same way in a relational database. I would have a table, and in the table I would rows with a primary key for each invoice. I'm going to have customers going to be a table, and I'll have a row here and a row here. So one of the ways I think about it is as if the rows in a relational database go backward in time, and all of the events are sitting behind that. So rather than summing up and throwing away the differences, we keep the history of everything we put into that row. Does that make sense? Right. Okay. So we have our core log, which is just like our write-ahead log in the database. We have our categories, which are like our tables. Then we have an instance or stream per item that has a series of events. So this is the structure we're building up to model our data in our system. So now let's talk about tables. So when you go back to Cod in the original papers about relational databases and relational systems, he starts talking about tuples. And all a tuple is a set of related data. So this row is a tuple. Just so you can define them in most languages now. I have three things, I want them all to go together. And what we do in a relational database is we take the tuples, we give them schemas, and we group those tuples by schema, right? And we call that a table. That's all that is. And then in relational databases, we have really amazing set operations and a very strong query language that lets us pull data from multiple tables together and produce things. Who here is familiar with third normal form versus first normal form? A little bit, one or two? So in a nutshell, third normal form is what you normally see when you see a database diagram with all the small tables that are related together. That's called third normal form, and all it means is don't repeat data. Put repeating data in a separate table and reference it rather than duplicating it in your table. That's it. First normal form is where you duplicate all the data so each row is by itself. First normal data is very good for reports because the reports don't have to do joins. Your table generally matches your screen or your report. Third normal form is very good for saving data, for efficiency, for being very tight. So, this is an example of a third normal form version of our customers and our invoices, right? Where I have a simple customer table, right, with an ID and a tuple. And then I have another table, invoices, with a primary ID. And then it's related to payment status, and it's related to the line items, right? So this is a third normal form structure. And you can see that I've got different schemas here for each table. What I want to do first, if I'm moving from this relational model to an event-driven model, is I need to find my categories. Right? And I said before that categories were like tables, but they're more like super tables. Because what it's going to be is that each root table is going to be a category. And I'm going to say that the events that go into the invoice streams have to match one of these schemas. Because we don't restrict the events that go into a stream to be of one type. They all have to be in the same set of schemas for the category, right? But they're not all the same event, right? So I can have this schema and this schema and this schema, right? What I'm actually going to start doing is one step further from there. Let's take a look at this. I'm going to take a look at my CRUD operations on the database. So I'm going to take my thermal form, find my categories. I'm then going to take my updates, my inserts, my deletes, and I'm going to model each one of them. So if I go back to here, we're going to start off with customer, right? Really simple. ID, name, type, payment terms. In the category customer, I have two streams, customer 1, customer 2. I take the insert operation, I give it a name. And the name of my insert operation becomes the name of my event. So rather insert into customer, it's add customer, or better yet, customer added, because we want past tense, right? And then I have the name, the three fields that we have there, right? Now you see I've got another one though, term extension negotiated, net 90. And here we see one of the big differences with these data models, right? Customer 1 and customer 2, when I look back at my relational model, all I see is current state. Right? If I put metadata on these events, which you should, of like when the payment terms were negotiated, then I'm going to know for each invoice issued against that customer what the payment terms were at the time that it was issued. I'm going to know that they started out net 30 and they negotiated net 90. So I don't lose any information. So what I'm really doing is I'm taking my relational data model, which is focused on efficiency and structure, and I'm saying, okay, I now want to be lossless, right? I don't want to lose the information of how I got here. And as we start working in distributed systems, having any service being able to pick up that full history, just like a stack trace on how did I get into this function, I know exactly how I got here, I know what business decision to make, and everything stays simple. Because we built that simple pipeline. We load the history, we make a decision, we write it down, and we move on. Right? So, now if we look at invoice, things get a little bit more complicated because we have multiple tables. We have invoice, add invoice. You see I got my primary key ID in here. Add invoice, date, goods, add a line item, add a line item. So you notice here, all of these events that before were going into different tables all go into one stream. But they have that same top level schema on them. And you can see that I have a payment received. If I look at invoice number 2, I see I've added the invoice, I've added the line item, second one, but then I removed the line item. So there's two things that are interesting here. One, I don't put the extra data here for the fields I'm not using from the table. I only need the reference ID. Remove line item 5. In the context, that gives me everything I need to know about what I'm doing. I don't need to repeat the data that's in line item 5 when I'm deleting it. So I haven't lost the fact that something was removed. Again, if I go back here, we can see invoice 2 only has one line item. Right? So we lost that information. Very often when you're looking at shopping cart apps, web applications, you want to know some customer gets to checkout with 5 things in their cart and they remove 2 and then they check out. What are the odds that if you gave them an opportunity to buy those 2 at a discount, they probably want them? Right? What most likely happened was like, oh, I don't want to spend $100. I only want to spend $80 today. But you still know that they wanted them. Right? Because we know when it was added and when it was removed, that tells us a lot. Also think about the case where someone puts something in their cart and then immediately removes it. They probably didn't really want that in the cart. Having the timeline of what happened gives us far more information and far more simplicity with, in fact, a richer data model. Because rather than just insert, delete, update, I've got names on these operations. Another classic example for the power of naming the operations is, what about a rename on a person? Right? People change their names for all sorts of reasons. Sometimes it's an administrative reason. Oh yeah, we typed in the database wrong. But that's very different than they got married. They had a legal change in their name. They had to update something. All of those are business things that are important to know about their status and what does it mean to change your name. In a regular system update, they get lost. The other thing that comes up in this model, so how many people here sort of like the model but think that it's going to wind up with a little bit too much data, a little bit too much storage? Yeah, one or two? So I always see this third normal form diagram up on the wall, right? But whenever I've actually gone in, I found that, well, yeah, this is our core third normal form, very tight. Well, then we have the audit tables. Oh, now we have the history tables. Oh, and then we got the reporting tables. And we send data over to the data warehouse. And so theoretically, we have this very tight model, but in real world systems, we're constantly copying and redisplaying that data in many other areas. So if instead, as we build our events, we focus on this third normal form concept, on just writing down what changed, what the new information is. I'm not repeating information, I'm writing it once, and I've got a lossless source of truth. That allows me to have the most succinct source of truth for my application, and I can build up those other models as I need them. I find that event source data models in production have a smaller footprint than their standardly designed relational database components in production after 2 or 3 years. Because they don't have these other tables. All these other things are built in and directly derived from the data model. So let's talk about how do we get data out. Is anyone here familiar with columnar data stores? Right, 1, 2, okay. So generally what happens is you look at it as a column with a series of updates and you collapse the column down to the last set of changes. This is the most simplistic form of creating a read model off of an event source system. In truth, we'll talk about the other cases later, but let's walk through this first. So if I have a series of event types with differing schemas, you can see here, that are all in a single category, I can create a union, which is every data element, every name. So what we're saying here is that the data elements in events that are in the same category should implicitly mean the same thing. So for all events in an invoice category, invoice ID represents the same data element, right? In a different category, invoice ID can be something completely different. But inside of a category, that always means the same thing. That means that you can calculate a union and then use it, and this is the most simplistic form, to say last value wins, right? Now, that's not going to work really well if we're building a banking application, right? Because I don't want to replace my balance with the $5 I just put in. I actually want to add it. So in real read models, we're going to have different operations based on the column to get the read model. But we're going to dynamically fold into that read model, and we're going to do it for the target source. So what you want to do is say, don't build read models for any reason. Say, I need this report, I need this web page, I need this thing. What data do I need? How do I calculate it from the downstream? And it's a simple fold. Just for each event, change it, modify it. Very often I'll put these in a relational database. Sometimes it could just be a text file. Any questions on that? Any questions on any of this? Okay. Okay. You have a table that fits into what? Then you just, it's an immutable store. The readers can read from multiple categories without limit. So you just read from both categories. You do a subscription to more than one stream, more than one category without any problem. You just read both categories and use both of them to produce your output. Does that make sense?
So the size of the table is the union of more than one stream.
Yes, absolutely. Because if you think about the model that we have, if I want to report saying what are all the invoices for Bob's Tires, I need to read from the customer category and the invoice category because all I have here is the ID. I'm not going to put the customer name in the invoice category. I'm going to use a foreign key for that. So I just read invoices, I go, okay, I need to know who customer 1 is, and I'll go read that and put that in the read model. And because the data is immutable, that means it's cache safe. Every change to cache will be an update to the model. Sort of tongue-in-cheek, I call that quantum consistency. So I can have a table of all my customer IDs and all of their current names in my relational database as part of my read model, and I know that will never be wrong, could be stale, but it's never going to be invalid unless I get a new event on a customer table or a customer stream, right? So I can safely use that to produce reproducible reports or web pages going forward. And it lets you scale out the read side as far as you want. Does that answer your question? All right.
Should we store also input together with events, especially in distributed systems? Because we might see situations that something happened,
Yep.
but let's admit, sometimes we make mistakes. And
Yep.
to understand why some event happened,
Mhm.
probably
Absolutely. So generally to figure out, what should we save about the input? How do we determine why an event occurred? So what I do in my metadata for all the events I do in a system, I have a causation and a correlation ID. And the causation is the direct parent, and the correlation is the root of the tree that caused this event to occur, because the source could be both commands and inputs and other events. That allows me to build a tree up of the full source. And so if you want to do that, what I do is I'll save the inputs in a separate store, because generally you don't need those for as long. Don't put those in your data model for your source of truth, but for your backtracing, why did this happen? Then I'll keep that there. So I'll keep the inputs of the commands as a separate log of the commands or triggers. Use correlation and causation IDs down through the system, so I'll know this user command resulted in this cascade of 30 events in the system. And now I know exactly why this changed. I can even use that to diagnose problems that are very difficult, like why did we have a wrong answer 2 weeks ago? Well, at the time, we thought this was true, and then that was corrected a week later, but this report was run at the time where that was true. And this is the only system and approach I've ever seen where I could give that answer to the business in any reasonable way. Because I've got the timestamp on every event of when it happened, and I have that record of when we changed our mind. So the other thing about the quantum consistency is, if you look at something like the Postgres write-ahead log, they have a monotonically increasing number, which is the log position. And monotonic is a fancy way of saying the number will always be bigger, but we're not going to say it's sequential. Whereas with event databases, you're going to get a sequential number. And in your distributed systems, this is incredibly powerful. Because as we saw before in those diagrams, I get an ordering 1, 2, 3, 4, 5. That means if I'm consuming events from a stream and I see 1, 2, 5, I know I missed 3 and 4. I know if I get 5 and I'm at 5 and I see 4, I can throw it away because I've already processed it. So it gives me very simple ways to deal with idempotency, very simple ways to deal with missing message detection. It makes the entire system architecture much simpler because I have that monotonically increasing, the atomically increasing number, which is different from the monotonic, which just says, hey, I'm ahead of the last one you saw. But if it doesn't have the full state, I don't know what happened in the middle. So this lets me have very targeted changes, consume them, and know my caches are at worst stale. This won't fix the, hey, I haven't gotten the last message yet, so you have to check for that, set up an SLA service, but it will solve missing, duplicate, and idempotency in a very simple way. So using that in production, what we're going to see is that, okay. That was supposed to be a little graphic that didn't happen. But so on the consumers, we see the events coming out in order, right? And then we have different systems that are going to be at different, because events propagate out through your system. They're not going to get everywhere at the same time. But what we want to make sure is that when we're making a decision, here and here, I have a service here that knows about event 10, which is the last thing committed on the stream. If I know I'm at 10, when I go to commit, it's going to work. But if I'm working on stale data and I'm on 8 and I try and commit, it's going to know that 2 more things have been committed or moved forward. And so it's going to know through that optimistic concurrency, oh, hey, you've got to go back, take a look at events 9 and 10. If they matter, apply them. If they don't matter, reapply your change. But now you can do it at position 10, and it'll work. Some examples where I don't want both of these events to go through, if event 8 is, if I'm here and I'm like, withdraw $10,000 from an ATM, and the other one is lock my card because I lost it, I don't want the log to accept both events. They go, cool, your card's locked, and we authorize you to the withdrawal. They change the state. So that's how we can use that, consistently. The other thing about this is why we want fine-grained streams. I want all the events for this invoice. I don't want to lock on all invoices. I don't want to have a partition that has tens of thousands of events in it. I want a stream that has like 30 events. I want the stream for this invoice so I have the most efficient locking and the most efficient throughput in the system, right? And if we look at this index here, so we can do it on any one of these 3, then we can do it all stream, individual stream, other things. Looking at this in the large, we want the source of truth database, which is this event source database, to be for an application. These represent applications. This represents your distributed event bus. That could be Kafka, that could be Kinesis. This is your public bus. So event sourcing, saving the state, is about this application. It should then produce, through an anti-corruption layer, a public event to publish on the wire for everyone else. So The same way you would never want another team in your company to directly use the tables in your private schema, because as soon as you come around to make a change, you're going to break their application, and all of a sudden you can't move forward. You're going to want them to use a public schema and not directly your tables. You don't want your private events, the data on the inside for your application, to be used publicly. Same, just like we're designing a private and a public API. Private, you want small, tight events, exactly what changed. Public, you want that personal form. You want to have all the data so your consumer doesn't call back to you. You know? So you can have 15 events here that are getting something ready, and then once it's committed and it's done, you just publish the fact that it's done out on your public bus to be consumed by other people. Some best practices: keep it sparse. Keep it sparse when you're running events, only what changed. Have your read models pull things together for how you want to consume it. Flag fields and nullable fields are generally a sign that you didn't model what actually happened, and you're folding more than one change type into a single event. Just like you have like hierarchy and table in relational databases. It's not a good idea. First start with having every single type of change have its own name. Model your process history. How did we get here? That's what this is all about. What was the history to get where we are, not where are we right now? Application surrogate key for you. Basically use keys. Use the customer ID. Use a surrogate key. Don't use a natural key. Enforce those in the application. And don't put any display data in your events. Pull that in through other sources. Don't put the customer name in an invoice paid event. Right? Just as I need to show the customer name, I should pull that from the customer table that owns that data. Last thoughts. So data retention is that we are going to be building up data over time. We will need to do a data retention policy. We have to do this in all systems. The pattern to look for is closing the books just like accounting. At the end of every accounting year, they say the books are final, last year is closed, you have to move on, right? You can do the same thing with your event source data. You just say, I'm going to shut down this, I'm going to start a new one, I'm going to open all of these things in the new one. And that's how we do our data management. But that's no different from any type of data system. Anytime you look like you're going to have a 10,000, 100,000 events a stream, look at refactoring that down to something smaller. You want a smaller lock-in transaction. Personal information in GDPR, separate out personal information from your system information. You might want to forget that customer 952 was Joe Brown, but you want your system to be able to work with customer 952 going forward. The only way that works is to segregate that data in advance and keep it so you can drop it while the system moves forward with unknown customer. Log scope and public and private, we just talked about. Data needs to be for your application and not for everyone that can possibly consume it. Any follow-up questions? Sure.
How would happen recovery after outages? I have seen situations when data stream continuously goes,
Yep.
but processing layer could go down. So
Right.
this application does not work. So after 12 hours, we have big amount of events.
Yep.
So one case is process all data.
Right.
So basically, we would need 12 hours of processing, or we need somehow to show the latest state. Are any workarounds or tips how to show like real life data, real time stream without recompute distributing all events?
So generally, what I will do is I'll have multiple things processing on the stream. And if you do have that kind of real-time input, I'll do snapshots at certain points in the stream. So you only have to go back to the snapshot and then read forward. But that requires multiple different layers to get to that current state. Oftentimes, like when you're looking at like video systems, you don't need to process all the intervening frames. So if you make your system understand what can be skipped to get a current view, that's another way. So either snapshotting or understanding what do you need to know to get to current state. The other thing which you can do is you have a burstable or scalable processing layer that can work in parallel. It can often process that stream faster than real time to catch you up so you're not waiting 12 hours to get there. So that's the three different ways.
How does the transactions work? For example, if there are multiple microservices
Yep.
and the underlying storage is like event sources.
So you want to make sure that your store to do this, you can use multiple different storage mechanisms to do this, but you want to make sure whatever you're using is a database in that it gives you ACID transactions on commits. So what you want is the events being written to any one stream to be committed transactionally, and you generally want the rest of the system to consume those events after the database. So you want to actually have a subscription listening to new events and publishing and having consumers listen to only committed data from the database. You retry. The rule is if it isn't saved in the database, it wasn't processed. So committing to the database is when the system recognized this occurred or this was decided. The fact that microservice decided doesn't mean anything until it's transactionally committed and everybody else can read it and it's part of the immutable history. And then by having that concurrency, you'll know if you have two competing services both trying to do this update in a hot scenario, only one can win. Because they're both have been read up to position X. They're trying to put in X plus 1. One of them will win, one will lose. So it lets it become a safe operation in a dynamically scalable environment. And I have time for one more question?
Unfortunately, no.
Okay.
Maybe if we got other questions, if we can maybe do them offline, because
Sure.
we have a very short break before the next session.
All right.
So we want to make.
Thank you all very much. Really appreciate it. I will be around all at the conference for the next 2 days. Come and find me. I've got to go do something right now, or I would wait for questions. But thank you very much.